So let's do some examples. Let's look at a spherical conductor.
As often as we use it.
Exactly. Our spherical conductors, remember, when equilibrium has been reached, all of the excess charge is on the surface. So our spherical conductor is going to have a surface charge density of eta and a radius of big R. So eta is the charge density of our sphere. Big R is the radius of the actual sphere. So this black sphere I've drawn is the actual conductor that has the charge on it. What I would like to do is to find the equations that describe the electric field outside of the sphere and inside of the sphere.
Is it a hollow sphere? Well, it's conductors.
Doesn't matter if it's hollow or not. It's a conductor, so all the excess charge will be on the surface. Whether it's hollow or solid, it doesn't matter. Okay, so we're using Gauss's law. Remember, we have the two conditions we need to meet. If we can draw an imaginary surface, that we call it the Gaussian surface. We can draw a surface that includes the point we're interested in finding the electric field at. We need to draw it so that the field would have the same value everywhere on the surface, and draw it so the electric field is parallel to the area vector. Then flux simplifies nicely down to be simply E times A. But we also know that flux is equal to the charge enclosed by the surface over epsilon naught. So we're going to relate the two in finding the electric field. So for example, outside, what that means is I want to find a field somewhere out there. I'm just choosing an arbitrary point right now. So someplace outside of the physical sphere. I'm going to say the radius, the distance from the center of our sphere out to the point we're interested in. I'm going to call that little r. Okay. So what I want to do is I want to draw a Gaussian surface, an imaginary surface, that we can look at the flux through. The surface needs to be symmetric to the object we're looking at. So since our actual object is a sphere, then the surface I need to draw needs to be a sphere as well. And I want to draw it so that it includes that point we're interested in. So this is called the Gaussian surface. It's just an imaginary surface, but it is the surface that we're going to look at the flux through.
So the inner sphere is the sphere of the object. The outer sphere is the sphere of how far out the charge.
How far out we want to know the field. So where we want to know the value of the electric field at. So the black one, the inner one, yes, is the actual conductor, the actual object that has the charge on it. The red one, the outer one, is the imaginary surface that we're drawing to look at the flux. So the flux. Flux, we've satisfied the conditions. The electric field will be uniform. It will have the same value everywhere on the surface that I've drawn, because we're centered on that spherical conductor. And the field is parallel to the area vector. They're both pointing radially outwards. So the flux will be simply E times A. A being the area of the Gaussian surface specifically, the area of the one we're finding the flux through. So we need the area of this red one that we've drawn. Since it's a sphere, surface area of a sphere is 4 pi. We need to use the radius of the Gaussian surface, so little r squared. So flux will be E times the 4 pi r squared.
And E is the fundamental unit of charge?
No, capital E is the electric field, whatever the electric field happens to be. We're looking for E. Our other equation for flux is Q enclosed over epsilon naught. So we need to know how much charge in coulombs is inside this this Gaussian surface we've drawn. Now, we stated up front that this sphere has a surface charge density of eta. So somehow, from eta, we need to get Q. We can't simply say eta over epsilon naught. That wouldn't be valid, because this has to be charge in coulombs. So how can we find the actual amount of charge inside this surface we've drawn? Not divide by area. Multiply by area. Eta remembers the ratio of charge per area. Now we have to be careful. The area of what? This guy?
The sphere on the inside.
This guy. Why not this guy?
Because that's not actually part of
Because
it.
that doesn't
That's
have
outside
any
the sphere.
charge.
This isn't the object that's charged. Exactly right.
It's a reference.
It's the black one that has the charge on it. So the charge is eta times the area of the actual charged object. So eta times 4 pi big R squared. Because we need to know where the charge is actually located.
Can we just put K?
No.
No.
K is 1 over 4 pi epsilon naught, so unless you end up with that.
Never mind.
Questions on getting either of these two?
You're saying that on the top one, the big E is the one that we're trying to find.
We're trying to find that.
And on the bottom one, what's the little e?
That's a constant. Epsilon naught is a constant.
Is that the fundamental unit?
No. Little e like that would be the fundamental unit of charge. Questions on getting either of those? Well, these have to be equal. Flux, regardless of which way we find it, is the flux. There's a certain amount of flux through that Gaussian surface. So we can set them equal to each other. So the top one, set that equal to the bottom one. Four pi's actually cancel. So we get E is equal to eta big R squared over epsilon naught times little r squared. Keep in mind, big R represents the radius of the actual charged object, and little r represents the distance out to the point where we want to know the field. So the point we're interested in. This equation works as long as we're outside. So little r needs to be bigger than or equal to big R. It will work at the surface. So it works starting at the surface and working our way out. It will not work if we work our way in. It doesn't work inside the surface. By the way, this equation is the same thing as that equation, because eta times 4 pi r squared, eta times area is going to be charge. It's going to be Q. So this term is Q, meaning the total charge on the sphere. Bringing the 4 pi r squared down, 1 over 4 pi epsilon naught r squared. Same equation. We've just written it in terms of the surface charge density, rather than just the charge.
Permittivity constant.
Yes.
Isn't the permeability constant?
No, I can't remember.
Permeability of free space.
Epsilon naught.
Permeability constant on the test note shows U naught.
Yeah, I get the two mixed up.
Yeah.
Yeah, mu naught. So epsilon naught is the permittivity, and mu naught is the permeability.
Oh no, a V and an M.
Exactly. But I am never in this class going to ask you for the name of it. Just pull the value off the notes. It'll be good. Okay, questions on getting this equation? We good? Okay, inside. if we want to know the electric field inside, say at some point over here, I'm going to use little r again. Little r just meaning to the point we're interested in. But this time I have to draw it inside the sphere. That means I need to draw my Gaussian surface, my imaginary surface, inside the sphere. So the flux, in terms of E times A, is still E times 4 pi little r squared. The flux in terms of charge enclosed over epsilon naught. How much charge is inside this little sphere that I've drawn? If we're inside our conductor, how much net charge lies within that? If we have a surface charge density, that means all the excess charge is on the surface. That leaves how much excess charge for the middle?
0.
None. So Q enclosed is 0. 0 over anything is 0. So when we set these equal to each other, we find the electric field is 0. That is valid everywhere inside of our sphere. So at any point smaller than the actual dimensions of the sphere, the electric field will be 0. And that ends up being the case for any conductor at all. All conductors in equilibrium, the excess charge lies on the surface. So you only end up with a surface charge density. That leaves no net charge inside, so that means the electric field will have to be 0 inside.
Wait, how did you get the Q, E, and C over E naught equaling the other coming to 0?
Because there's no net charge in here.
Okay, and so the Q, E, and C was 0.
Right. Exactly right. So the charge enclosed was 0, which makes that whole term go to 0. Questions?
So it's always 0 inside, so why do we even...
Inside a conductor.
Oh.
It's not 0 if it's not a conductor. Unless it only has a surface charge density.